everyone. Today we're looking at notes J-2, finding inverses. But before we begin with that, we actually have a pretty big lesson that we need to refresh from Algebra 2. So today's pre-cal lesson is pretty Algebra 2 heavy, so I definitely want to make sure that you remember this Algebra 2 knowledge before we begin. It's not going to take me too long to talk through it. It might take you a little while to write it, so just make sure you pause as you need to so that way you can pay attention and understand and grasp these concepts so you're not confused. So remember from Algebra 2 when we talked about inverses, okay, and specifically when we worked with quadratics. Okay, so remember from J-1, this quadratic is not a one-to-one function. Therefore, the inverse will not be a function. And we saw that in Algebra 2. When you find the inverse of the parent function x squared, y equals x squared, or f of x equals x squared, the inverse, hence the notation here, was not a function. The inverse was plus or minus square root of x. So we had the positive square root of x and the negative square root of x graph. And obviously that's not a function. So when this wasn't one-to-one, the function, or the inverse, was not a function, right? So what we did in Algebra 2 is we looked at just pieces of the quadratic graph. So we restricted the quadratic graph to either just be the right or just be the left. When we restricted to the right, we said x is greater than or equal to 0. Remember, we found the middle, which in the case of a quadratic is the vertex. We found the middle. Okay, we found where the vertex was, we found that line of symmetry, and then we either chose to keep the right or we chose to keep the left. And like I said, when we chose to keep the right, that produced the inverse function. Now this is a one-to-one function, so this inverse will also be a function, and that function would be just the positive version of the square root graph. However, when we restricted the quadratic to only keep the left, when we said x is less than 0, less than or equal to 0, excuse me, when we only kept the left, the inverse function was the negative square root graph, right? So do you remember doing that in Algebra 2? And both of these are, in fact, functions because, remember, the original function that we found the inverse of was one-to-one. So therefore, the inverse was a function. When the given function wasn't one-to-one, the inverse was not a function. Okay, so hopefully you kind of remember that. And then let's talk about going the other way around. So then we also talked about what if you're given the function a square root graph? So in this case, you're given the positive square root graph, and in this case, you're given the negative square root graph. What would the inverse look like? Well, when you do the algebra, you would just get x squared, and then you would have to decide, okay, well, I know it's not the whole x squared graph, I just keep a piece of it. And the piece that you keep for the positive square root graph, it just goes right back to this. The piece that you keep for the positive square root graph is the right piece. So that's when x is greater than or equal to 0. And if you're given f of x equals negative square root of x as your original function, and you're asked to find the inverse, then algebraically you would just get x squared, and you'd have to say, oh, but I don't keep the whole graph. Since this is the negative square root graph, I keep the left piece of that quadratic graph. So hopefully that's bringing back some memories for you. So what we need to take from that for today's lesson is that when we're finding inverses, you will see that even-powered functions will be restricted. And if they're not, then that poses a problem, and we're going to talk about that. So essentially what you should get from this is we will restrict even-powered functions. Now, the only even-powered function we worked with in Algebra 2 was quadratic, but we might be working with x to the 4th, so quartic, or x to the 6th, any even-powered function. So notice the restriction always goes with the even-powered function. It never went with the square root. So notice the restrictions went with the even-powered function. Okay, and another thing to say is that while we don't quote-unquote restrict the square root graph, it was essentially restricted because we either kept only the positive or the negative version. But we're going to get into that here in just a bit. So essentially restrict only even-powered functions. Okay, so pause me if you need to. We're moving on, okay? So let's get to the problems for today. So the directions here, we have to be very cautious of what we're being asked always. So the directions here say find the inverse function. Okay, so here in this case, we would have a problem because that's not a function, right? So we need to talk about that when we go through these problems. So in this particular problem, f of x equals the cube root of x plus 1, we don't have an issue because this isn't going to produce an even-powered function. This is odd index. So with odd indices, we don't have as much of an issue. So when you're asked to find the inverse function algebraically, remember from Algebra 2, you switch x and y, then solve for new y. So this goes for any problem. You always switch x and y and solve for the new y. So that's your directions for finding the inverse. Okay, so this is y. F of x is like y. So we'll call it x equals cube root of y plus 1. So I switched x and y. Now I'm going to solve for my new y. Okay, so now to get y by itself, I'm going to raise both sides to the third power. Okay, so this would be x to the third equals, this will just become y plus 1. And then I'm going to jump this plus 1 across the equal sign. So this will look like x cubed minus 1 equals y. So I've solved for my new y. And now this is a cubic graph. It is a function. Everything seems to clear. So we just say the inverse function of x equals x cubed minus 1. So I don't need to worry about anything special when I'm dealing with those odd powered functions. They're easy to deal with. It's the even powered functions that I need to worry about. So we're not there yet. We're still not even there yet because now we're still dealing with an odd powered function. So your odd powered functions are going to be 1 to 1. So you don't need to worry about them. It's just those even functions that aren't. So again, we have an odd powered function. So we're going to switch x and y. So this is going to be x equals y to the 5th plus 3. Okay. So I'm trying to get y completely by itself. So I'm going to jump over that plus 3. So this is going to look like x minus 3 equals y to the 5th. And then I'm going to get rid of the 5th power, I'm going to bring in the 5th root. Okay, 5th root. All right, so, oops, wrong color. So the 5th root of x minus 3 equals y. Here's a big note. You don't bring in absolute value, in other words, the plus or minus, right? So I didn't say that the 5th root of y to the 5th is the absolute value of y. I don't bring in the absolute value, which changes to that plus or minus, when you bring in an odd number root. Okay, so again, it's those even powers and even roots that you need to be worried about, not odd. Okay, so we don't have absolute value here. We don't have plus or minus situation. So other than sticking that f function notation, f inverse of x equals 5th root of x minus 3, make sure the whole x minus 3 is under the radical. Other than that, you're done with this problem. Okay, all right, so that's number 2. Number 3, f of x equals x to the 5/7. My pen looks like it's running out. Okay, so let's switch x and y. So this will be x equals y to the 5/7. Okay, so how do you get y by itself? Raise both sides to the reciprocal power. Okay. So the reciprocal of 5/7 is 7/5. Again, we are working with odd powers, odd roots here. 7 over 5, that's all odd. Okay, so we're good. No issues yet, right? So we just have x to the 7/5 equals, and then here, remember our rule when we have power to power is multiply. So when you multiply 5/7 times 7/5, you just get 1. So y to the 1st, right? That synthesis is really bothering me. This doesn't look very clean. Hopefully y'all can see it. I think so. Okay, so now last thing, is this a function? Yeah, we don't have any nonsense. We didn't have an even power, even root. So we are good. No nonsense. All right, ready for the nonsense. Number 4. So now that we've got the hang of the odd power, odd roots, let's bring in an even power problem. Okay, so let's talk real quick. So if this is the given problem, remember, find the inverse function. All of these so far, we have found the inverse function. Cubic, that's a function. Fifth root, that's a function. This is, in fact, a function, okay? So here's the deal. If if an even powered function is not restricted, the inverse would not be a function. We just talked about that, y'all. Okay, so we saw that earlier. We saw when this even powered function wasn't restricted, the inverse wasn't a function. When it's restricted, when we're only looking at half, we're good. We have an inverse that's a function, but when it's not, we don't have an inverse that's a function. So reading these directions, if it said find the inverse function, and this was just this and it didn't have this, you would say not possible. It's not possible. There is no inverse function, not unless it's restricted. So if an even powered function is not restricted, the inverse would not be a function. Therefore, given these directions, find the inverse function, you would say not possible. So just be aware. You would say an inverse function does not exist. It's just an inverse. It's not a function. Okay, so just be very cautious of that. And that's why we had that whole conversation at the beginning. Okay, so switch your x and y. So x equals y squared plus 3. Okay, so move over the plus 3. So this is x minus 3 equals y squared. Okay, so now here's where we square root both sides. And hopefully a red flashing light is going off in your head because now we have an even index. Okay, that 2, that's a square root. There's an implied 2 there. So we do get absolute value. Okay, we didn't bring in absolute value whenever you bring in an odd root, but whenever you bring in an even root, we have that absolute value. Therefore, to get rid of the absolute value, that's where we get the plus or minus to get y completely by itself. So remember that. And again, make sure you're cautious to make sure that radical doesn't fall short and it covers the 3 every single time, okay? Make sure it doesn't fall out or else it wouldn't mean the same thing. So then here, this isn't a function. Remember, this is a square root graph. Remember from Algebra 2, this is a square root graph that shifted right 1, 2, 3. And if we have the positive square root graph and the negative square root graph, that's not a function. Okay, so what we have to look at is to determine which one we choose. We're going to look. We're going to look at this to determine what do we choose. Do we choose plus or do we choose minus? Well, x is less than or equal to 0 is the left side of the graph. Therefore, that corresponds, the left side of the graph corresponds with the bottom. That corresponds with the negative. So our inverse function will be the negative square root graph, okay? Because this was less than, because it was to the left. So hopefully, based on the pictures you saw earlier, that's making sense to you. Okay, we only have 2 more, so bear with me. Bear with me, 2 more. Okay, number 5. Number 5 is actually a rational graph. So something we only had a little bit of time in Algebra 2 to talk about, and we're going to deepen your knowledge quite a bit in this class. So we've got this rational graph, okay? No even powers, right? So we should be good. No even powers. So this will become x equals 2y plus 7 over y plus 3. Okay, remember, once we switch x and y, the goal is to solve for that new y. So since we have a fraction, what we're going to do here is we're going to cross multiply, but be very cautious. When you multiply this x times the denominator, it distributes to both terms. So make sure that looks like xy plus 3x equals, and then of course 1 times the numerator here would just stay 2y plus 7. Remember, the goal is to get the y by itself. Well, we've got a y in this term and a y in this term. I really need to gather the terms that have y in them. So I'm going to move this term that has y across this side. Since this term doesn't have a y in it, I'm going to move it across this side. So I'm going to have xy minus 2y equals negative 3x plus 7. And then so that way I have a single y, I will factor out y because I don't want two y's. I want y by itself alone, a single y. So I'd factor out y and I'd have x minus 2, do you agree with me? Because the GCF was y, equals negative 3x plus 7. And then here to get y completely by itself, divide both sides by x minus 2. Okay, so here, x minus 2 over x minus 2 simplifies to 1. I get y equals negative 3x plus 7, and really no reason to keep the x minus 2 in parentheses. And your final step, since there was no shenanigans, this is going to be a function. We're good to go. Okay, nothing weird. We're just going to write that inverse function notation. Okay, because that was a one-to-one graph to begin with, so the inverse is a function. Okay, last problem. You know I got to throw in a couple of more shenanigans for you, right? So 6, fun graph. F of x equals negative 2 over the square root of 3x. So we have that even index. We have that even index situation. And look, because we have the negative 2, now I know the square root's in the radical, and that does make the graph look pretty funky. It actually, we'll let you see it real quick. It's negative 2 and then square root of 3x. So the graph does look kind of funny. It is kind of looks like a square root graph, but that negative there tells us when we restrict, because we're going to have to restrict, we're dealing with an even index, that we're going to keep, that negative tells us we're going to keep the left side. Okay, so we will talk about that here in just a moment. So let's first do the algebra. So still the algebra is the same. So switch x and y, so x equals negative 2 over square root 3y. Okay, like we did before, since this is a fraction situation, we're going to put x over 1. We're going to cross multiply. So we have x times, oh, well, you know what? Before we do that, let's do this. Okay, actually, I changed my mind because that's looking ugly. What we're going to do first is we're going to get rid of the square root. It would be in our best interest first to go ahead and square both sides. Okay, so let's do that first. As I look at that problem, I'm like, oh, no, that's going to be ugly. So x squared equals, and then this is going to become 4 because you square the numerator and then you square the denominator. So 4 over 3y. When you square the square root of 3y, it just becomes 3y. Now it would be a good idea. You could still cross multiply first, but then when you raise both sides to the second power, it does get a little funky. Okay, so now let's cross multiply. So we would have, let's just write it, 3x squared y, when you multiply those, equals 4. Now remember, our goal is to get y by itself. So I want to divide by 3x squared, divide by 3x squared. So this is going to look like y equals 4 over 3x squared. So it's not a quadratic graph per se, but it is an even powered function, okay? Because the x squared is in the denominator, and this is what I've been harping on you about this whole time, is this is not a quadratic because the x squared is in the denominator. It's actually a rational function. So the picture is different, but it's still an even power. So we still have the situation where we're going to have to restrict. So here's the question. Okay, when we restrict to make this a function, well, it already is a function, but we still want to restrict like we did. Here's where I want to show you. Remember here when we were given a square root graph, based on if it was the positive or negative version, based on that, we knew if we were going to keep the right or the left. Okay, so here, remember we started with the negative version of the square root graph. So we're going to keep the left, okay? So how we will say, there hasn't been a shift, there's just been a stretch or shrink. There hasn't been a shift left or right, so our middle would still be x equals 0. So we're going to keep the left, so that's going to be x is less than 0. Why for this one do I not put less than or equal to? I'm like being silent for a reason. I want you to think about it. So I said before, when you were starting out with a negative square root type graph, again, this isn't quite a square root graph, it's similar, but the square root of x is in the denominator, so it's not quite, but it acts the same. So again, when you were starting with a negative, we kept the left, so we kept what was less than or equal to. Here, why am I saying I'm only keeping less than, not less than or equal to? Because now we're dealing with a rational. And we can't say x is less than or equal to 0, because if we have 0 in the denominator, that would cause all kinds of bad math things to happen, right? So for the rational graphs, you don't say or equal to 0 whenever you're given this situation, because you can't have 0 in the denominator. So hopefully that wasn't too terrible of a lesson for you today. Remember, the key is, where is it? Restrict even-powered functions. So I should even probably write it here. Restrict even-powered functions. So you notice the only function I had to restrict myself, everything else was pre-restricted, was this one, because we had an even-powered function.